So now moving on to Module 9.2, we'll be dealing with transient conduction, looking at finite difference equations right here. So the thing we want to talk about now is the fact that analytical solutions to transient problems are restricted to simple geometries and boundary conditions, such as 1D cases that are considered in the preceding section. So these are really simple cases to really understand that theory, see how we apply our equations there. But even for some 2D and 3D simple ones, analytical solutions are still possible, even getting some of the 2D and 3D geometries. We saw a little bit of that as well. But in reality, that's not always the case. In many cases, the geometry or boundary conditions preclude the use of these analytical techniques that we've talked about previously here, and we must identify some finite different methods in order to solve these right here. So in this module here, in the section module 9.2, we're going to take a look at some of these explicit and implicit forms of the finite difference solutions for these transient conduction problems. So within this module here, we'll look at the finite difference method, talk about energy balance and the finite difference approximation for storage term, and we'll also look at the explicit and implicit method of solution right there. So this one here, we'll go over the theory of all these topics above, talk about our key equations, go through some practical applications, and then actually go through some problem solving together as well. So for our Module 9.2, this is going to be looking at our transient conduction still, and now we're going to be looking at our finite difference equations and solutions. As related to our textbook, this is wrapping up our Chapter 5, taking a look at Section 510. So let's get into the topic of this finite difference method. So what is the finite difference method? We've looked at this a little bit before. So just a refresher, this finite difference method is an approximate method. So again, this is an approximate method. That's something that's important to note there. And this is for determining temperatures at discrete nodal points of the physical system and at discrete times during the transient process. So within this, what we want to do is establish a procedure for how we can go about in a methodic way for solving these type of problems using this finite difference method. So for our procedure, what we want to do is we want to represent the physical system by a nodal network. Now within this nodal network, we want to utilize this MN notation to designate the location of these discrete points within the network. And then we want to discretize the problem in time. So we're doing this as time as well by designating a time increment now, our delta t, and expressing the time as the relationship that we see here, that time is equal to p delta t, where p assumes integral values right here from p is equal to 0, 1, 2, and keeps going on. So going back to our mn, so again, the way to think of this MN notation right here is the same way as like a Cartesian coordinate system. We're using our x, y, and that designates the location of where these things are from an origin point. So this is similar to what we did earlier in this module as well, utilizing that same MN notation. So now once we've represented this physical system by a nodal network, the next thing we want to do is go back to our energy balance method and use that to obtain finite difference equation for each node of an unknown temperature. So we're looking at each node within that nodal network and using the energy balance method to obtain that finite difference equation. So once we have those equations, the next step would be to actually go through and solve those equations. So solving the resulting set of equations for the nodal temperatures at, again, our time right here, time is equal to delta T, 2 times delta T, 3 times delta T, and so on. So now one thing we want to ask ourselves here is what is represented by this value right here for this variable here? We see T to the P subscript M comma N. Well, let's break this down a little bit. The superscript P that we see right up top here is used to denote the time dependence of our temperature. And the time derivative expressed in terms of the difference in temperatures as associated with the new P plus 1 and the previous P times right there. So that's how we're denoting between those. So hence the calculations must be performed at successive times separated by the interval of our delta T. And just as a finite difference solution restricts temperature determination to discrete points in space, it also restricts to discrete points in time as well. So as we were looking through that procedure that we wrote up on the previous slide, one thing that we noticed is that there was an energy balance equation we need to deal with there. So now for our energy storage term, let's take a look at this energy balance and our finite difference approximation for the storage term right there. So if we think about our energy balance right here, for any nodal region, the energy balance is going to be given by this relationship shown in our equation 5.84, where we have our E dot in plus our E dot G is equal to our EST, where E dot in is our rate of energy transferred into a control volume in units of watts. Our E dot G is the rate of energy generation in watts, and our EST is the rate of increase of energy stored within the control volume in units of watts as well. Now, according to convection, all heat flow is going to be assumed to be in the region. So looking at the discretization of temperature variation with time, we have this equation 5.77. So this equation here shows us that our partial of temperature with respect to time evaluated at some mn is approximately equal to, now there's that variable we saw before for temperature right there, our temperature mn at p plus 1 minus our temperature mn at p right there. So then this is with time right there, and we recall that superscript had to deal with time points right there. And this is all divided by our delta t value right there. So now let's take a look at our finite difference form of this storage term right there. So this says now right here that our E dot st of mn right there at that position right there is equal to our rho Vc, our density, our volume, and our specific heat, times now we have this fraction over here. We're on the numerator. Again, we have that same term we have up here, that temperature superscript P plus 1 of Mn minus the temperature at P of Mn right there, all divided by that delta T right there, which is exactly from this equation up here, 5.77. Now we have the existence of two options for the time at which all other terms in the energy balance are evaluated here. This is either a P or a P plus 1. Now just let's note here, the P is used to denote the time dependence of that temperature, and the time derivation is expressed in terms of the difference in temperatures associated with the new P plus 1 and the previous P times. So looking back at the procedure we were talking about, we realized the next step would be to look at our solution for the finite difference method. So let's take a look at our explicit method right here. So the explicit method of solution right here. Now what we want to consider with this is that all other terms in our energy balance are going to be evaluated at the preceding time. Recall now that preceding time corresponds to that P that we talked about. Now with this here, we can think of our equation 5.77 is going to be termed as a forward difference approximation. So that's another way that we could hear this relationship that we see in this equation 5.77. So now let's take a look at an example. So for this example here, what we have is a two-dimensional conduction for an interior node with a delta x equals to delta y. So a pretty simple case here for a nodal network right there. So we can see we have an interior node. So there's our interior node right there, our Mn. And we can see that our delta x right here is equal to our delta y for this. So for this, now we can go to our governing equation, 5.79 in our textbook right here. We have that variable t right here to the p plus 1 mn. So this is equal to our Fourier number, which again we recall is our dimensionless time right there, times now we have this t to the p of m plus 1n. So we can go m plus 1n, so the same way we went through the nodal network, that corresponds to this node right there, plus our t to the p m minus 1n, that corresponds to this node right here now. Then we have plus t to the p m n plus 1. T to the p m n plus 1 corresponds to this node right there. And last we have our temperature here, t to the p m comma n minus 1, which goes to this node right here, m comma n minus 1. And this is now plus 1 minus 4 times our Fourier number right here times that temperature there, t to the p of m n for that center node right there. Now, a thing to note when we're talking about our Fourier number here that we see in this equation 5.79 is that our Fourier number is equal to our term alpha times delta t all over our delta x squared, which is our finite difference form for our Fourier number. Now, for unknown nodal temperatures at a new time, a t is equal to a p plus 1 over delta t. These are determined explicitly by known nodal temperatures at the preceding time when our t is equal to our p delta t right there. Hence the term explicit solution right there. So we solve by marching in time. So continuing on with our explicit method here, we want to ask ourselves now, how is the solution accuracy going to be affected by our choices for that delta x and our delta t? Well, thinking back to how we looked at the nodal network before, the finer the grid, the more accurate it is. So the smaller our delta x is right there, that small step in between, the sizing between our nodes right there, then that's going to make it more accurate there. And there is going to be a relationship between our delta x and our delta t, so very small time steps may be required for these large number of nodes. As we decrease the size of in between our nodes, or delta x, it's going to increase the number of nodes right there. And for the larger number of nodes, we're going to need a smaller time step for that there. So both of those are going to combine together to give us a more accurate solution. Now we also have the stability criterion that we can take a look at here. So this is determined by requiring the coefficient for the node of interest at the previous time to be greater than or equal to 0, and that's going to dictate our stability criterion. So now for a finite difference equation in the form that we see right here, which we recall now this is related back to our equation 5.79 that we looked at earlier. So we have that t to the p plus 1 mn right there is equal to all of this here, plus now this term in front of our t to the p mn right there. This term is an a right here. So for this relationship for my stability criterion, our a must be greater than or equal to 0. So we can see that there for a two-dimensional interior node, this would be right here, which we just saw that right there from that equation 5.79, 1 minus 4 times our Fourier number is greater than or equal to 0, or we can rewrite that right there and say our Fourier number must be less than or equal to 1/4. So now with this relationship here that our Fourier number needs to be less than or equal to 1/4, and we have this relationship here for our finite difference for our Fourier number right there, that our Fourier number is equal to our alpha delta t over our delta x squared. We can rearrange this here. Now we can say that our delta t must be less than or equal to our delta x squared all over our 4 times alpha. Next, let's take a look at our table 5.3, where we can look at our finite difference equations for some common nodal regions. So looking back at our table 5.3 in our textbook here, we have here our transient two-dimensional finite difference equations. For the case, pay attention here, that our delta x is equal to delta y. So we can see these different configurations right here. So we have configuration 1 where we have that interior node, like we just looked at in our example there. We also have now an interior node node in interior corner with convection. So we see this right here, and we can see our convection term right there. And in third case here, we have a node at a planar surface with convection right there. So there's our planar surface. There's convection right there. And last for 4, right here, we have a node at an external corner with convection right there. So we can see associated with each of these, we have a finite difference equation. So we can see for the interior node, we have this equation here, 5.79. For our node at our internal corner with convection, we have 5.88, given by this relationship here. Same thing here for 3, the node at a planar surface with convection. We have this equation 5.90 right there. And for the last one here, we have our 5.92 for our node at exterior corner with convection, given by this relationship right here. Now we can also see our stability criterion right here. So that's where we came up with this right here. We just saw that our Fourier number must be less than or equal to 1/4. That's 5.83 because we were dealing with that interior node. Now they have these again for the other 3 criteria as well for all these stability criterion right there. Now we also have an equation for each of these for our implicit method as well. So now let's talk about that implicit method of solution. So rather than an explicit, now we're going to take a look at this implicit method here. And this addresses the limitations of the explicit method, allowing for larger time steps. So all other terms of our energy balance are evaluated at a new time corresponding to now our p plus 1. So now our equation 5.77 is then termed the backward difference approximation. So now let's take a look at an example here. So we'll look at that same type of example here where we have a two-dimensional conduction for an interior node with that same delta x is equal to delta y. So the same thing we looked at here for our explicit, but now we're going to take a look at it for our implicit method solution right here. So now what we have here is we have this general equation that we can see from our textbook, which is equation 5.95 right here. And we can again see way over here, it's a little bit different now. We can see we have 1 plus 4 times our Fourier number, times now we have this value here for our temperature at p plus 1 mn right there. So there's our mn right there at a time of p plus 1 right there, minus our Fourier's number times. Now we have the temperature at each of those other nodes at that time of p plus 1 right there. We go over m plus 1n, mn plus 1, m minus 1n, and mn minus 1 right there for all 4 of those nodes. So the temperature at the time p plus 1 for all those. So that right there is all equal to the temperature of our center node right there at time of p. Now, if we're looking at a system of n finite difference equations for some number n unknown nodal temperatures, this can be solved using our matrix inversion or our Gauss Seidel iteration right there. So that's a method that we can use to solve these if we're dealing with a system of those finite difference equations. So one thing to note here, though, is that the solution is going to be unconditionally stable, which is nice for this compared to our explicit method right there. And now we can go over to our table 5.3 again and reference here for our finite difference equations for other common nodal regions as well. So now let's take a look at our marching solution here. So for a transient temperature distribution, this can be determined by a marching solution where we begin with here our known initial conditions. So we can start out with our known initial conditions here, and we can see we can march down through. So we have our delta T, our 2 times delta T, our 3 times delta T, all the way down here till we get to our steady state right there. And from that, we can get all of this other information we're going through. So we're marching through by these values of our delta T right there for this solution. So now let's apply this theory and these governing equations to an example problem here. So we'll take a look at this problem 5.109, where we have a thin rod and they give us a diameter D, and they also tell us it's initially in equilibrium with its surroundings, and a large vacuum enclosure that has a temperature of our T surround. So we can look down here, there's our T surround right there. Now suddenly an electrical current right here, this is I of A right there, and amps right there, is passed through the rod, having an electrical resistivity that they give us as our rho sub E, and emissivity here of epsilon right there. Now, other pertinent thermophysical properties are identified in the sketch down here below, so we have our given diagram we can get that information from. What they're asking us to do is to derive a transient finite difference equation for our node M right there. So you can see there's our M. There's our M plus 1. There's our M minus 1 right there. So now we can go through and utilize some of those governing equations in order to solve for this and derive a the transient finite difference equation for that center node M right there. So now from that problem statement, we can do a little bit of a summary here. So they're asking us to come up with a derivation of the explicit form of the finite difference equation for a nodal point in a thin electrically conducting rod confined by a vacuum enclosure. So that's what we have down here. So there's that diagram again there with all the information on that diagram included right here. So what's known? We know it's a thin rod. We know it has a diameter D. And we know it's initially in equilibrium with its surroundings, which is our temperature T surround right there, and it suddenly passes a current I. The rod is also in a vacuum enclosure and has the prescribed electrical resistivity, our rho sub E, and the other thermophysical properties that we can see in our diagram. So we redraw this diagram out by hand down here. There's a temperature of our surroundings. We can see all of our information here. There's our node M, our M plus 1, our M minus 1, the distance between those both being delta X, so they're equal distance apart. Our X moving in this direction here. There's our current going through there. There's all of our other values right there for this rod itself. And there's our temperature at that center node M right there. So what do we need to find? We need to find our transient finite difference equation for this node M at the center there. So now let's go through our hand solution for this problem.
We're now going to take a look at example problem 5.109. In this problem, we have a thin rod with a known diameter D that is initially in equilibrium with its surroundings. It's a large vacuum enclosure at a temperature T surround. Suddenly, an electrical current I is passed through the rod, having an electrical resistivity of rho sub E and an emissivity of epsilon. The other pertinent thermophysical properties are identified below in the sketch. We need to derive a transient finite difference equation for node M. So here's node M. Here's our schematic down below, so we can see what we have here. Here's our current coming through our rod with diameter D, and over here we have the surrounding temperature T surround there. We can see also we have our geometry here. We have a delta X between node M and M minus 1, and between M and M plus 1, that same delta X there. There's our epsilon value there. There's our T sub M, and here's our other properties as well for this rod. So now that we've had an opportunity to look through the problem statement and the given schematic diagram, the next step is to write this out in the format that we're used to. So one of the things I want to do first off is to figure out which variables are used within this problem. So over here on the left, I have all of my variable names here and the actual names of what each of these variables are. So we have D, capital D is the diameter of our rod. We have T sub surround, which is the temperatures of the surroundings. We have capital I as our current. We have our rho sub E, which is our electrical resistivity. We have epsilon, which is our emissivity. We have rho, which is our density. We have C, which is our specific heat. And we have K, which is our thermal conductivity. And then we have T sub M, which is our temperature at node M. So once we have all these down, we've clearly defined what our variable names are, what they are in practical terms. What we want to do is redraw out our given schematic diagram in a slightly simplified form, where we also include all of these variables that we just talked about on the left. So we have our current I over here, we have our specific heat, our K, our densities over here, we have each of our nodes, M, M-1, and M+1, and our temperatures, along with our geometries for this given diagram. So now that we have all of this in front of us, what we want to do is figure out, okay, what are they asking us to solve for? And in this case here, what they ask us to find is the transient finite difference equation for node M. So that's what we want to do for our solution. But before we start our solution, what we want to do is go through and figure out what our assumptions are to simplify this problem down. So we're going to assume three different things here. First thing we're going to assume is 1D transient conduction in the rod. We're going to assume that surroundings are much larger than the rod, and we're also going to assume constant properties. So this gives us our first sheet where, again, we have all of our given information, what they're asking us to find, what our assumptions are, and our simplified given diagram. So we're going to reference back to this as we go through our solution to the problem. So now that we've had the time to write out our first format page with all of our given variables, our simplified schematic diagram, and what we're looking for along with our assumptions, the next step is to think about our solution. So for our solution for this particular problem, the first thing we want to do is apply the conservation of energy to a nodal region of a volume. So volume is equal to area times change in distance over here, where for our specific rod in this problem here, our A sub c is given to us by the relationship of pi d squared over 4, where d is the diameter. So we go back to that first page, we look at our capital D as the diameter of the rod there. So this is now our area term that we can plug back in to calculate our volume. So now we actually need to come down to our general equation for our conservation of energy, or our energy balance equation here. So in this we have E in minus E out plus EG is equal to EST, where this over here, our EIN, is the rate of energy into the control volume. Our E out is our rate of energy out of the control volume. Our E sub G is the rate of energy generation. And our E sub ST over here is the rate of increase of energy stored within the control volume. So we can see the dots above each of these here. This corresponds to the rate. So let's take a look at E sub G, our rate of energy generation. So our E sub G is given to us by this relationship from our text here, that E sub G, our rate of energy generation, is equal to our I squared times RE, where RE is given to us as rho sub E times delta X over AC, where our delta X is given to us in the problem statement, the distance between the nodes, and A sub C we've now defined by this equation up here, pi d squared over 4. Next, we want to take a look at our forward difference representations. So what we're going to want to do is plug into the energy balance. So from our energy balance equation from up above here, we can now start plugging in our terms for our specific problem related to the nodes over here. So in this nodal region, again, we have our T sub m, our T sub m minus 1, and our T sub m plus 1. We know there's a delta x distance in between each of those. So what we can see here, if we go back to our energy balance equation, what do we have going in? So going in, we have QA, QB. There's our QA and QB going in to know T sub m that we're interested in here. Now what's coming out is Q rad. So Q rad is coming out. And then we have our E sub G right here, which again is our rate of energy generation. And again, we have an equation for this here, so we can plug this in for our E sub G over here. And this is equal to our rate of increase of energy stored within the control volume, our E sub ST, is now given by this relationship here, which is the finite difference form of the storage term. So this is our energy storage term in finite difference form over here, rho VC. Then we have the temperature at the node given here, minus temperature there, divided by our time, our change in time, delta T, where now we have a rho given to us in the problem statement. Our volume we have from the equation up above here, based on our area and our delta X, and then we have our C given to us in the problem statement there. So now we're set up for our forward difference representation. So now that we have a simplified version or a general form for our straightforward difference representation of our energy balance equation here, what we want to do is start going in and plugging in for each of the individual terms within this equation here. So that's where we're going to take a look back in reference to equation 1.2 on page 4 of the book here, and we go through our definition for our heat flux and our heat rate, and we want to go through and plug all of those in now for our variables within this energy balance equation. So from these given equations from the first chapter at the beginning of our textbook, we can see that our Q sub A for our specific problem is given to us as K times this A sub T times the temperature difference of node M-1 and node M, all divided by the distance between them, delta X. Our Q sub B is similar, is K A sub C times the temperature difference from our M+1 node minus our node M over here, all divided by delta X as well. And then for our radiation term, Q radiation, again given from those same equations in the beginning of chapter 1 in our textbook, we have our emissivity times A sub S times our sigma times our temperature difference of node M minus the temperature of the surroundings, both to the 4th power there. This comes from equations 1.8 and 1.0 on page 10, again at the beginning of this chapter, where A sub S for this particular one here is given to us as pi dl. And then we can come over here now to our E sub G term. E sub G is equal to I squared. We replace our RE with this relationship here, rho E delta X over AC that we saw before. And now we have an equation for each one of these variables that go into our energy balance equation. But again, I chose to write out this full energy balance equation in a more general, simplified form, just so it's easier to see, and then go through for each of these and provide the specific formulation from these equations from the beginning of chapter 1. If we were to stick all of these right in at once, it becomes very messy and hard to follow, so I chose to do it separately like this here. So now that we have an equation for each of the terms within the energy balance equation expanded out from our equations at the beginning of chapter 1, the next thing I want to do is go back to that general form of the energy balance equation and plug in all these variables for this more long involved equation. I'm trying to take my time, draw things out neatly so I can clearly understand what's going on. So I take each of my terms. I have my Q sub A term that I plug in right here, which again is K A sub C times the temperature difference between node M-1 and node M divided by delta X, plus now my Q sub B term over here, which is K A sub C times the temperature at node M+1 minus the temperature at node M divided by the distance between them, delta X. And then I have my radiation term, Q rad, which is equal to epsilon pi delta X sigma times the temperature difference to the 4th between the node M and the surrounding temperature, plus now I have on the right hand side over here my E sub G term, which is I squared times rho sub E delta X over AC. And this is all equal now to the right hand side of our equation for the energy balance here, which when we do this out is rho C AC delta X, where our specific heat area in delta X is equal to the volume term over here, times the temperature difference between node M and of P+1 minus node M at P divided by time, delta T there. So the next thing we want to do is kind of go through this and rearrange and simplify. So the first step in this here is to divide each term by this relationship here where we have this guy and this here to get that away from the right hand side of the equation, so we can hopefully just leave the temperatures over there on the right hand side. So that's what we're doing down here. I'll leave this up for a little bit for you guys to look at here, but all I've done is take and divide the right side and the left side by this rho C A delta X over my delta T term to again just leave this over here in terms of my delta T's on the right hand side. Change difference in the temperatures. So that's what we do here, divide through, we end up with this relationship here. And we can see when we divide through by this term here, our A sub C's will cancel. We'll end up with this relationship down here. So now that we've gone through and divided the first term by this rho C AC delta X over delta T, we now want to do it for the second term. This is our Q sub B term. We already did it through for our Q sub A term. We'll do it now through our Q sub B term. Divide this through by rho C AC delta X over delta T. We go here again. We see that our A sub C's cancel when we divide through by that. And for our second term, we're now left with this here. So now we move on to our third term. So now we divide our third term by that same denominator from the right-hand side of our equation, rho C AC delta X over delta T. We do this down through here, and we see that we have a delta X that cancels in the numerator and the denominator. which then yields us with this relationship here for our third term. So now we have our first, our second, and our third term. So this is our second term from our energy balance equation. This is our third term from our energy balance equation. And our first term was given on the previous page. So now that we've divided the first, second, and third terms of our energy balance equation by the denominator, we do it again for our fourth term. So our fourth term from our energy balance equation, recall, was I squared rho E delta X over AC. So we divide that through by that denominator over here, rho C, AC, delta X, delta T. We can see the delta X's are going to cancel again. So for our fourth term here, we now have the I squared rho E over A squared C times delta T over rho C as our final solution for our fourth term here. So then we take a look at our right-hand side of the equation after this here. And obviously, if we divide through by this on our right-hand side of the equation here, this is going to cancel, this is going to cancel, and we're just left with this change in temperature we want to solve for this guy right here for our solution. So now that we've gone through term by term and divided by that denominator to eliminate that from the right-hand side of the equation, we now need to combine these all back together in one long, very involved equation in order to finish our solution. So we have over here, once we divide through by the denominator, here's our term for Q sub A. Over here, we have our K divided by rho C times delta T over delta X squared times our temperature difference between node M minus 1 and node M. And we have our Q sub B term, which is K over rho C times delta T over delta X squared times our temperature difference between node M plus 1 and node M. And we have our radiation term over here, where we have our epsilon times pi d sigma over AC times delta T over rho C times our temperature difference between node M to the fourth minus our surrounding temperature to the fourth there. And we have our E sub G term over here, where we have our I squared rho E all over our area squared A sub C squared times delta T over rho C. So that takes care of our left-hand side of the equation. On the right-hand side of the equation, our EST term, now that we've divided by that denominator, we now have this relationship of the difference between Tm to the P plus 1 minus Tm to P. So now we want to go through and solve for this term here, our temperature at M is P plus 1. We do rearrange. Basically, we just add this guy over here to the equation over here on the right. So now we've gone through and solved it for this variable here. And if we go back to the problem statement, what they asked us to solve for, they wanted us to derive the transient finite difference equation for node M. So that's exactly what this is here once we've solved it for this variable here. This whole term here is exactly what they asked us to solve for, which is the transient finite difference equation for node M.